All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. First of all, thank you guys for being flexible today as I get over my sickness. Wasn't able to come to campus today. I am planning on coming back on Thursday. There is a meeting that I need to be on campus for, so I will be back. But for today, I'm home resting up. So thank you guys for being flexible and meeting on Zoom. Okay, so the plan for today is we're going to be working on our lecture notes on impedance. And so we started the discussion last week. I think we got through the linearization of the 1D equations. And so we'll continue on with that derivation today and kind of see where that goes. I do have a couple of announcements today. So if you noticed last night, there were a couple assignments that were posted, one of which, you should already be aware about. And so that is the midterm project. So remember, the geometry, the paths, the segmentations, and the model for your midterm project is going to be due on April 12th. And so I officially put up the submissions for that. So if you're done with the project, you can go ahead and upload your Vascular project there. Okay. The other thing that I posted was your next homework assignment, which is homework 3. And so homework 3 is about the 1D modeling and the impedance stuff that we're going over this week, right? And that is also going to be due on April 12th. And so that's the the next week after this one is spring break, and then the week after that, April 12th, that's Friday. So it's going to be so both assignments are going to be due the Friday after we come back from spring break. And so you have a little bit over 3 weeks, a little bit less than 3 weeks to do everything. Okay. Okay, so the reason I wanted to get that homework assignment in is that we do have our midterm exam that's going to take place after we come back from spring break as well. Not that first week, of course, but the week after that. So I want to make sure you get some practice, just because it's been a while. It's been a while since you guys have turned in the lump parameter modeling assignment. So I want to make sure you guys get some. You guys are kind of staying on top of the lecture material. Okay. All right, so that's all my announcements. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off last Thursday. Okay, so the topic that we were going over last Thursday was impedance of vascular trees. And so, this whole unit, and I kind of want to take I kind of want to remind you guys of kind of the big picture because, we're about to jump into a lot of math once again. And so kind of once you kind of start talking about kind of the mathematical details, it's kind of hard to remember kind of the big picture stuff. So the whole idea with this unit is the fact that as blood kind of flows through the cardiovascular system, it's going to encounter some resistance to its flow, right? So there's going to be factors that make it difficult or impede the flow from progressing from one end to the other. Okay. So it's not a free process, right? And so it takes energy, it takes effort from the heart to kind of pump blood through your system. Okay. And essentially, what the heart is hoping to overcome is it all these factors here that impede blood flow, right? And this is true for any kind of fluid dynamical system, right? So you think about the water that's flowing through your faucet, flowing through your pipes, right? There's some energy losses, there are some factors that impede its progress. And so you need pumps or some energy energy adding factors to overcome those issues. Okay. And so the whole idea with this unit is to kind of get a bigger understanding or kind of a more complete picture of what all these factors are, and kind of develop a mathematical model to model these. Okay. So some of these factors here are things like viscous resistance. Okay. So that's akin to like some of the friction forces that occur in the cardiovascular system. Okay. We have things like inertia. Okay. It takes energy to put anything in motion, and so inertia is going to be an important factor that causes impedance to blood flow. So those things are kind of ubiquitous throughout all of fluid flow. But one particular factor that's unique about blood flow that's you don't really see it in a lot of other systems is this pressure wave propagation phenomenon. My cat's being a little shit. Okay, get out of here. All right. So the pressure wave propagation basically has to do with the fact that whenever the heart beats, it sends a pressure wave along the vessel walls, right? So this has to do with the fact that your vessel walls are deformable, right? So we talked about this a bit kind of in arterial biomechanics. So those pressure waves actually go to the end of the tree and actually reflect backwards. And as those pressure waves reflect backwards, this also introduces some impedance to the flow, right? Okay. And so any discussion or any mention of impedance or resistance or things that the heart needs to overcome needs to include this pressure wave propagation effect. Otherwise, it's kind of an incomplete picture. Okay. All right. So that's kind of the motivation. And so mathematically, where we were last time was that kind of the vessel or kind of the method that we're going to be using to analyze this impedance is our 1D equations. Okay. Okay. So our starting point was our 1D equations that we kind of spent, so long to try to derive their values. Okay. And what we did last time was we linearized them to make them a little bit easier to work with. Okay. Because one thing that you probably saw, last time was that when you have, our 1D equations, even though they are a big simplification from, the full Navier-Stokes equations, they're still pretty difficult to solve because they are nonlinear PDEs. And so if you're solving it by code, if you're solving by code, it's not really that big an issue. You can do it. But if you're going to be solving them by hand, which is, what we're going to be doing here, we need to make them a little bit easier to work with. Otherwise, it's going to be almost impossible to do that. Okay. And so what we did last time was we linearized the equation. So, just to kind of summarize what we found was that if we took some of the nonlinear terms and averaged them around kind of their reference value, then we can either cross out some of the nonlinear terms or make some assumptions to make things simple. Okay. And so what we ended up with is the following equations. Okay? And so we end up with partial A, partial T, plus partial Q, partial Z is equal to 0. Okay. So that was our continuity equation or conservation of mass. So this equation we actually didn't make any changes to because it was already linear. Okay. The main change that we made was to the momentum equation, where we eliminated some terms and we made some other terms more simple. Okay. So our momentum equation looked like the following: so partial q partial t plus a naught over rho times partial p partial z is equal to minus 8 mu, 8 pi, 8 pi nu times q over a naught. So this is our linearized momentum equation. Okay, so that's the starting point from today. So what we're going to do from here is we're going to find solutions to these equations here. And what we're going to find is that the solutions to these equations match the linear wave equation, which is which we know a lot about because that's a very heavily studied equation in applied mathematics. Okay. Okay, but that was just kind of a summary of kind of what we're doing in this section and where we're going. Any questions on this so far? Okay. Okay, so let's go ahead and go from here. Okay. Okay, so let's find solutions to these equations. So, unfortunately, what I have here is kind of another fairly lengthy mathematical derivation. But at the end of this, we're going to get kind of a process or an algorithm that we're going to use. Okay, and that's essentially what you're going to be applying in the home. So this derivation, still important. So, don't tune out, don't play games on your phone. But I think this one's a little bit more usable, a little bit. We end up with something a little bit more practical at the end compared to the 1D equations. Okay. So the way this solution works is that we're going to kind of cheat a little bit because we kind of know, or we kind of know ahead of time, kind of where we want to go, right? And so we kind of know already that eventually these equations are going to turn into kind of like a wave equation type of solution. Okay. And so the first step is to kind of make these equations kind of look similar to like a wave equation. Okay. And so our first step is actually going to be to define a new variable, which is something we're going to do quite often today. Okay. So let's define. Okay. We're going to define a new variable called C naught squared. Okay. And so this C naught here is that's going to be the wave speed. Okay. Notice how we're using a very similar notation to something like the speed of light or speed of sound, right? So both of those have use this denotation c, and that's very intentional, right? And so what we're going to get here is kind of similar to kind of how sound waves propagate and how light waves propagate as well. Okay, so we're going to define this new variable, and we're going to define it in terms of some of the variables that we already have in our equation. Okay, and so for us, that's going to be a naught divided by rho times the partial derivative of the pressure P by A. Okay, so that's partial P partial A. Okay. Okay. So the reason we're doing this is that if you look at our two equations here, if you look at our conservation of mass equation, if we look at our momentum equation, we have essentially three variables, right? On the continuity equation, we have the cross-sectional area A and the flow rate Q. Okay, so we have A and Q. And then on the momentum equation, we have Q and P. Okay. For the momentum equation, we've basically kind of linearized out the area. Okay. So the first thing we want to do is we want to get these equations in a form which only has two variables. Okay. So we want to eventually eliminate the area variable from the continuity equation. Okay. So that's kind of the main reason why we're introducing this. Okay. So the a variable in the continuity equation takes the form of partial a, partial t. Okay. And so we can kind of break this up using the chain rule. Okay. And so what we can say is that this is equal to partial a, partial p multiplied by partial p, partial t. Okay. Okay, so let's do a little bit of algebraic rearrangement here. So again, this is, some people would consider this kind of mathematical sacrilege. I call it a pro gamer move. Okay, so we want to kind of manipulate this equation so that we get this variable right here. Okay, so we want to basically get partial p, partial a from this equation right here, right? So if you notice, we have one term here that's kind of similar, right? So we have partial a, partial p. And so if we kind of flip it on its head, then we get partial p, partial a. Okay, so we want to manipulate to get this. Okay. Okay. And so basically, if we manipulate this, then what we get is um, let's go the other way actually. Let's manipulate this top equation to get partial a, partial p. Sorry about that. So we want to manipulate this top equation to get not partial p, partial a, but partial a, partial p, and then plug it in for here. Okay. Okay, so if we manipulate that top equation there, and so what we get from this is we divide both sides by a naught and multiply by rho. And so what we get is rho times c naught squared divided by a naught is equal to partial p, partial a. Okay. And so if we take the reciprocal of this, okay, then what we get is partial a, partial p is equal to a naught over rho c naught squared. Okay. All right. So now what we can do is we can plug this in for this expression inside our chain. Okay. Okay. And so if we do that, we get partial a, partial t is equal to a naught over rho c naught squared times partial p, partial t. Okay. All right. So now that we have this expression here, we can plug this back into our continuity and eliminate the area from our continuity equation. Okay. And so if we do that, we plug back in, we plug in for basically partial a, partial t. Okay, so we're plugging in for this term right here. Okay. And so we do that, we come back down here. What we get is a naught over rho c naught squared, partial p, partial t, plus partial q, partial t, partial p, partial z, excuse me. Okay. and all this is equal to 0. Okay. All right, so that's where we are with this equation. Okay. All right, so all we've done so far was we've kind of introduced this concept of a wave speed, and we say that it's you know it's some ratio of the area and the pressure, and we use that wave speed to eliminate area from our continuity equation. Okay, so now our continuity equation is a function of P and Q. Okay, and so we'll go from here. Right? Any questions on what we've done so far? Okay. All right. So we're looking good. All right. So we want this to interact together with the momentum equation, right? And so if we look at the derivatives that we have here, we have partial P partial T and partial Q partial Z, right? If we look at the derivatives on our momentum equation, we have partial Q partial T and partial P partial Z, okay? So these are actually opposites of each other. And so if you look at them, and so we're taking the derivative of flow rate with respect to time and the derivative of pressure with respect to Z, okay? That's kind of opposite of what we have here. And so we want to basically use these equations to eliminate one of the unknowns, okay? Okay. The problem with doing this though is that it's not as simple as kind of an algebraic relationship because we're talking about derivatives here. So we need to take additional derivatives to kind of match the derivatives. Okay. So you can do this a couple different ways. The way I'm going to do it is I'm going to primarily eliminate the pressure term from both equations. Okay. So let's take this equation that we just found. Okay. And let's take the derivative of this entire expression with respect to Z. Okay. Okay, so what we're going to have here is we have partial Z, this entire equation here. So of A naught or rho C naught squared, partial P, partial T, plus partial Q, partial Z is equal to 0. Okay. So differentiation is a linear operator, so we're going to apply it to both terms. Okay. And then all the constants, we can just kind of leave them alone. So A naught, rho, C naught, those are all constants. Okay. We apply that Z derivative to P, we end up with the cross derivative. So we have partial squared P over partial Z, partial T, plus we have a double derivative of Q with respect to Z. So partial squared Q, partial Z squared is equal to 0. Okay. Okay. So that's good. Now, so that we can eliminate the P from our equation, let's take our momentum equation and take the derivative of that one with respect to T. So you have partial t of our momentum equation, which we had up here. Okay. That's going to be partial t of partial q, partial t, plus a naught over rho, partial p, partial z is equal to minus 8 pi nu q over a naught. Okay. So just like we did in the equation above it, we're going to apply the derivative to each term here. So we have 3 terms to apply it to. And so we have partial squared q, partial t squared, plus a naught over rho, partial squared p over partial z, partial t is equal to minus 8 pi mu divided by a naught, partial q, partial t. Okay. Okay. So let me box this equation here too. Okay. We still have a ways to go, but I'm only boxing here just to kind of highlight things. Okay. All right. And so if you look at this term in our kind of modified conservation of mass equation, and we look at this term right here, okay, they look very similar. In fact, they're almost identical. The only thing that's different here is that the top equation there is multiplied by the top term there is divided by C naught. Okay. And so we can almost eliminate the pressure from these equations if we kind of deal with that factor, right? So let's take this top equation just so that the 2 terms are equal. Let's multiply this top equation by C naught squared. Okay. So that we can get both of both the terms highlighted in green to be the same. Okay, so let me go ahead and do that down here. And so if we multiply this entire top equation by C naught squared, we get a naught over rho, partial squared p, partial z, partial t, plus C naught squared, partial squared q, partial z squared is equal to 0. Okay. Okay. Now, if we look at this equation here, and we look at this equation up here, okay, if we subtract these 2 equations, okay, so we take the first equation minus the second equation, so subtraction of both equations. Okay. Subtracting both equations is going to eliminate the pressure term from both. And so we'll have just one equation that we can solve for Q. Okay. All right, so let's go ahead and subtract it. Okay, so we're going to do the first equation minus the second equation. And so doing so, we're going to subtract the left-hand sides first. And so the left-hand sides are both going to have this, a naught over rho, partial squared p, partial z, partial t. Okay, so both of those terms are going to be eliminated. And what's left here is just everything, all derivatives with respect to q. So we have partial squared q, partial t squared, okay, minus c naught, partial squared q over partial z squared, okay. This is equal to minus 8 pi nu over a naught, partial q, partial t. Okay. And then if you want to make this in the classic form, traditionally the double derivative with respect to time is on the other side of the equation. Okay. And so if we put this kind of in standard form, it would look kind of something like this. And so we have q squared, a partial squared q partial t squared is equal to c naught partial squared q partial z squared minus 8 pi nu over a naught partial q partial t. Okay. All right. So a lot of calculus, a lot of algebra later. We end up with something like this. Okay. If you've taken something like 438 or 538, hopefully this equation here looks familiar to you. If you haven't taken it, it's okay. We're going to solve for the equation or solve for the solution now. But this type of equation here, where you have kind of two, you have one variable here. We have q, and we have a double derivative with respect to time. We have a double derivative with respect to space. Okay. There's only one spatial derivative here, so that's in the z direction. And then finally, we have an additional term here, which is just one derivative with respect to time. Okay. Of course, we have some constants in there. We have some coefficients that change the behavior a little bit. But the main behavior of the equation is still the same, right? So this pattern, when you have these three particular terms, okay, in an equation, this is what's known as the classical wave equation. Okay. And actually a lot of applied math. And so, from anything like acoustics to electromagnetic waves, they have, they follow this equation to some degree, okay, especially in the 1D case. And so this is a very, very famous, very, very well studied equation. And so the fact that, we were able to manipulate our blood flow equations to get it in this form is a really good thing, right? And it means that we can analyze it using everything that we know about wave equations up to this point. Okay. All right. Any questions on how we got to this point here? Okay, good. All right. So we have this equation here. Okay. And now that we know that we have a classical wave equation, we can go about finding its solution. All right. So the good news is that, one thing about the classical wave equation is that it has its solution can be found by separation of variables. Okay. So you guys are all going to get a crash course on how to solve for solutions to PDEs, right? A very simple PDE, but a very important one for applied math in general. Okay. So a separable equation means that we have two independent variables here. We have both z and t, right? And so a separable solution means that both of those factors are kind of completely separate from each other, right? So that means our solution q, okay, which is a function of z and t. So this is our flow rate solution. What it means for a solution to be separable is that we have one component that has to do with space. Okay. We have some function q1 of z that has to do with space. So this is the spatial component. Okay. And then this is going to be multiplied by the temporal component, or the time component. Okay. In particular, because we have the wave equation here, we kind of already know the form of the temporal component. Okay. And so the temporal component is going to be E I omega t. Okay, right? And so a separable solution means that, you can separate these two things out, right? And so there's not too much intermingling between them, right? So you have a spatial component, time component, you just multiply them together and you get your space-time solution. Okay? So the spatial component right now is an unknown function, so we do need to find this. Okay? The time component, if you look here, we're already kind of assuming a form for that time component, which is going to be a sinusoidal or pulsatile form. Okay? And so if you're unfamiliar with Euler's formula, basically this e to the I omega t is the same thing as cosine omega t plus I sine omega t. It's one of the classical kind of mathematical relationships. Okay. The reason we're choosing a sinusoidal form for t is because part of it is because we know that we're solving a wave equation, and so that's just kind of always the case for wave equations. But it makes sense given our physical system, right? So remember, the physical system that we're modeling at this point is a cardiovascular flow, right? And the thing with cardiovascular flow is that it's pulsatile in nature. Right? So we've gone over that kind of multiple times in this class already. The fact that the heart beats with a steady rhythm, you have the flow rate and the pressure that kind of go up and down, with the rhythm. Not perfectly like a sine wave, but it has a lot of similar characteristics, right? So we can kind of already infer that our time component here is going to be, sinusoidal or repeating or pulsatile to some degree. Okay. Um, so that kind of saves us a little bit of time, right? So if you were to solve this equation naturally, it would come out just naturally that the time component is sinusoidal. We're just kind of saving ourselves a little step here just by making that assumption just from the bat. Okay. Okay. So this is what our solution looks like. So our solution, which is a function of z and t, we can separate it out into a spatial component and a time component, right? So the time component, we kind of already know everything about it already. We already know its form, but we don't know what the spatial component looks like, okay? So what we need to do is we need to take this form, okay? And what we're going to do is we're going to plug it back into our governing equation up here, okay? Because we're going to plug it back into the wave equation. And what that's going to allow us to do is it's going to allow us to solve for Q1 of Z. Okay, so let's go ahead and do just that. Okay, and you'll kind of see the power of the separable form because once we take the derivatives, you'll see that it turns out pretty nicely. Okay, so let's plug into our form here. Right? Okay, so in our wave equation here, the first thing that we have is partial squared q partial t squared. Okay, so we're going to take the second derivative of this with respect to time. So you have partial squared partial t squared of q1 of z e to the I omega t. Okay. This is equal to c naught squared times the second derivative with respect to space of our assumed solution. Get partial squared partial z squared of q1 of z e to the I omega t. Okay. And then we have our viscous term here. So our viscous term is minus partial t, or minus 8 pi nu over a naught partial t of Q1 of Z e to the I omega t. Okay, so all I did for that part there was I just took our assumed solution here and plugged it back into our wave equation. Okay, so everywhere that I saw Q, I plugged in this form here, and we're about to carry out the derivatives. Okay, so let's carry out these derivatives, right? And so the fact that we have a separable solution here kind of simplifies our math a bit. Okay. All right, so first we have the second derivative of this with respect to time. And so, we're not taking derivatives with respect to z, so this term can just kind of pop out right in front, okay? And so this first term is going to be q1 of z, okay, multiplied by the second derivative of e to the I omega t, okay? And so we're going to use kind of chain rule twice here. So we have an I omega squared that comes out, okay? So we multiply by ei omega t. So that I omega squared there comes out from taking the derivative with respect to time twice. Okay. Next, we have this C naught term. So we have C naught squared. This time we're taking the derivative with respect to Z. And so in this case, the e to the I omega t pops out because, this part here is only a function of time. Okay. So we can pop that guy out in front because we're not taking derivative with respect to time. Okay. And so if we do that, we get C naught squared e to the I omega t multiplied by the second derivative of q1 with respect to z. So since q1 here is a function of just one variable, I'm just going to plug in just a regular derivative here. So d squared q1 dz squared, okay, minus. Then we have the last term there, which is a first derivative with respect to time. So this is an 8 pi nu over a naught. We take one derivative, we get I omega times q1 of z e to the I omega t. Okay. All right. So again, all I did in that part there was I just carried out the derivatives, and any kind of chain rule stuff that came out, we kind of did that as well. Okay. All right. Next step here is what you should see is that every single term here has this e to the I omega t, right? And so if every term here has that same expression, we can factor it out and cancel it. Okay. Right, so that's kind of why we chose that form, or another reason we chose that form, right? It's kind of convenient for the problem that we're solving. Okay. Okay. Next thing I'll do before the next line is that I'll notice here that this I omega squared here is I squared times omega squared. Okay. Where that I there represents an imaginary number. So an imaginary number, is a square root of -1. And so if we square I squared is just going to be -1. And so this is going to be equal to minus omega squared. Okay. Okay. And so if we apply all those things, we get minus omega squared q1 of z is equal to c naught d squared q1 dz squared minus 8 pi I times nu over a naught times omega q1 of z. Okay. C naught squared, sorry. Okay. All right. From here, we have some algebraic, things to kind of clean up here. So let's divide this entire equation by C naught squared. What I'm also going to do is I'm going to move everything here to the right-hand side of the equation. Okay. All right, so this is kind of just cleanup at this point, just to kind of help get things into a nicer form. Okay. And so if we do that, what we get here is 0 is equal to d squared q1 dz squared. Okay. Now that second order derivative is by itself because we divided everything by c naught squared. Okay. And then we have a minus 1 over c naught squared multiplied by 8 pi I nu omega divided by a naught minus omega squared q1 of z. Okay. Okay. I'm going to make another substitution here, and so this term here that I've kind of grouped together in pink, it's kind of an eyesore, right? So it's kind of a mess to look at. But if you look at all the terms there, everything there is a constant, right? C naught, the wave speed, we're assuming is constant. 8 pi, constant. I, constant. Viscosity, constant. Omega, for all intents and purposes, is a constant. It doesn't depend on z. And a naught, which is our reference area, is a constant as well. Okay. And so if everything there is a constant, we could continue to carry it around. It's just a little bit cumbersome to write. And so just to make our life a little bit easier, and also just to kind of make it easier to find a solution, let's just kind of replace this with a new variable that kind of takes its value. We're going to replace this with, and so just to kind of keep things consistent with, with ODE terminology, we're going to find a new variable lambda. Okay. And we're going to say lambda squared is equal to everything in here. So lambda squared is equal to 1 over c naught squared times 8 pi I nu omega divided by a naught minus omega squared. Okay. So the only reason we're doing this is just for our sanity, just because we're going to be writing this a lot soon. Okay. And so if we do that, we get 0 is equal to d squared q1 d z squared minus lambda squared q1 of z. Okay. All right. It's a lot of work. So a lot of PDEs. If you've taken PDEs before, maybe you've seen this before, but I think it's something that you never really get used to. I'm definitely, reading my notes very closely as we're kind of doing this derivation. Okay. So we end up with this equation here. Okay. So it's a second order differential equation. But if you notice here that unlike everything else that we've seen, this right here is an ordinary differential equation. Okay. It only involves one unknown, which is Q1, and it only has one independent variable, which is Z. Okay. So we've effectively kind of, through our separation of variables, we've effectively eliminated t from the equation. Okay. If you notice something about the strategy here, this is pretty standard for solving kind of complex problems, that you kind of, one by one, you kind of eliminate all of the complexity. So you eliminate all the extra variables, you eliminate all the extra solutions, right? You're going to bring them back eventually, right? And so it's not like they're forgotten, but you kind of like, whittle down the complexity of the equation until you get something that you can actually solve by hand. Okay. And that's what we've done here. So we've started with a very complex kind of partial differential equation that involved, pressure, cross-sectional area, flow. Our independent variables were time and space, right? So it was something that was very, very difficult to solve by hand. Then through this whole process here, all this math, all this stuff here, now we've gotten something that we can actually solve by hand. Okay. Okay. So you can solve this, with whatever kind of method that you like. I think kind of the standard way is to use kind of the characteristic equation. Okay. But this is something that we can solve by hand. Okay. So the solution to this ODE by using the characteristic equation is we have this equation here has an exponential solution. So we have Q1 of Z is equal to C1 e to the minus lambda Z plus C2 e to the positive lambda Z. All right. So now we have something, right? So now that we have a solution for the spatial component, we can now plug this in to get our, our solution for Q of Z and T. Okay. Okay. Because remember, from our separation of variables, assumption here, we said that Q of Z and T is equal to the product of Q1 of Z, which is what we just solved for, and e to the I omega t. Okay. So we plug in our expression here for Q1 of Z, and we get C1 e to the minus lambda Z plus C2 e to the lambda Z. Okay. And all that is multiplied by e to the I omega t. Okay. All right. Any questions on this so far? Good. Okay. So of course, this does have the caveat of requiring two unknowns, C1 and C2. We'll deal with that in a second. But the next step here is to use this solution and solve for P. Okay. So let's go ahead and do that. Okay. So to do this, we're going to use our other equation, which is our continuity equation, right? So we haven't used that one just yet. But just like our flow rate, we need to assume a form of our pressure solution. Okay. And so, once again, we're going to kind of cheat a little bit. We kind of know a bit about the solution, but we're going to make the assumption that our pressure has the same form as our flow solution. So it's a fully separable solution. Okay. And that's kind of partially kind of due to knowing that, we know our pressure is also kind of a pulsatile solution. There's going to be some kind of wave phenomenon with it as well, right? So it makes sense that, our pressure solution is going to be a wave equation solution as well. Okay. And so what we're going to assume for this is P of Z and T is equal to P1 of Z, which again is going to be the spatial component multiplied by e to the I omega t, which is the temporal component. Okay. So same form, just different functions here. Right. So once again, we already know what our temporal component looks like. We know that it's going to be a sinusoid, e to the I omega t. We just need to solve for P1 of t, okay, which we're going to do through our continuity equation. Okay. So, just like we did for Q, we want a solution for P1 of Z, okay, the spatial component of the pressure solution. Okay, so let me go ahead and write out our continuity equation here. Okay, so our continuity equation in our linearized form was equal to A naught divided by rho C naught squared, okay, multiplied by partial P, partial T, plus partial Q, partial Z, that's equal to 0. Okay. All right, so we know Q. We can just plug in our solution for Q here. Okay. So Q is what we just found, prior to this. And then for P, we're going to plug in this expression right here. Okay. So same deal. So same deal as we did for the wave equation for Q. So we basically assumed a form for pressure, and we're just plugging into the solution and are plugging into the equation in order to get something that's solvable for P. Okay. Okay. So let's go ahead and do that. And so this is going to be A naught over rho C naught squared partial T of P1 of Z e to the I omega t, okay, plus partial Z of our flow equation, which is up here, okay. So this is going to be C1 e to the minus lambda t plus C2 e to the positive lambda t, or lambda z, excuse me, okay, multiplied by e to the I omega t. Okay. So let's go ahead and carry out our derivatives here. And so we take the derivative of the first term with respect to time. And so we have A naught over rho C naught squared times I omega P1 of Z e to the I omega t, okay, plus we're going to carry out the derivative of the second term with respect to Z. And so, because we have exponential terms here, the derivatives here are pretty straightforward. So we're just going to have lambdas that come out, okay? So we have plus, we have minus C1 lambda, e to the minus lambda z, plus C2 lambda, e to the lambda z, times e to the I omega t. Okay. And all this is equal to 0. Okay. So again, it looks like we have a mess here, but thankfully, there's no derivatives of P1 of z, so we can find this solution purely algebraically, which is really nice. Okay. Okay. So first thing we notice here is that we have e to the I omega t on both terms, just like we did for the wave equation. So we're going to go ahead and eliminate those. Okay. Then from here, we can just solve everything kind of just algebraically. Okay. 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 So we're going to isolate P1 of z, right? And so we're going to move the two terms to the other side. Okay. All right. And so if we do that, so this next part here is just algebra, just for the sake of time, I'm just going to go ahead and skip ahead. Okay. And so when we do that, we get P1 of z is equal to minus rho C naught squared times lambda divided by I omega A naught times quantity minus C1 e to the minus lambda z plus C2 e to the lambda z. Okay. All right. Any questions on this so far? Okay. All right. So through lots of trial and tribulations, another hour of just kind of pure math, we have our solutions to the wave equation. Although, with everything that we have so far and all of these variables here, it doesn't, I know it doesn't feel that satisfying because, we don't have an actual solution. We just have kind of a bunch of variables. Okay. But remember, we have, there's a lot of variables here, but just know that, all of this stuff here, these are just constants, right? And so essentially, when we apply this to a certain vessel, these are just going to be values that we plug in the parameters for. And so it's not that we don't care about them. It's kind of more that so we do care about them, right? But when you're doing kind of an analytical solution like this, which is kind of what we're doing, we're going through a lot of effort here to get an analytical solution. The parts that that are really kind of important are terms like these actually. Okay. And so you may have kind of done similar derivations in your other classes, right? And it's very easy to kind of get lost in kind of the alphabet soup of kind of all these variables and all these different things, right? And so a really important skill to kind of know in these kinds of situations is what's the most important thing, right? So what do we need to get out of this? What's the conclusion? What's the point, right? What's the point of doing all this math? What we're kind of most interested in here are kind of what are the terms here that depend on our variables, right? And so if you look at all of our other terms here, right? Essentially, this function here, or this equation, is a function of z, right? So what we're interested in here is, how does the pressure, depend on our z variable? Depend on z, and how does it depend on time as well? Okay. Ultimately, when you're doing kind of a long derivation like this, that's the most important thing to glean is, what are your variables of interest, and how do they change, right? Because that's honestly, that's the real value of doing an analytical solution, right? You could take this equation, and you can find a numerical solution for it. You can write a MATLAB code for it. You can do that just fine. We've done that before. Um, but with the numerical solution, unless you're very, very patient in terms of changing the variables, it's very hard to kind of look at it and find kind of general patterns, right? So the whole reason, and the whole reason you go through derivations is so that you can kind of highlight and kind of find, what's the general patterns, right? So how do things vary in a general sense, okay? And so, we go through these derivations. I know it's painful. It takes a lot of time. I try to go through kind of every step, but the important things to kind of take away is how do the variables kind of interact with each other, right? That's the value of an analytical solution. That's why mathematicians spend decades kind of doing this stuff is so that we can kind of get these equations, and kind of understand a little bit about how these systems behave. Right? And so in this particular case, we're looking at this and we're saying, wow, we have an exponential kind of relationship here with our pressure. Right? So the further along that we travel in z, we have these two exponential terms that kind of guide us. Right? Same thing for the flow rate. Right? So that's kind of the upshot here. Okay. Okay. So the last thing that I'll leave you with, before we sign off for today is it's not this general solution is nice. But in order for us to actually use it, we need to come up with values for C1 and C2. Okay. Okay. So traditionally, the way that we find these variables is that we apply boundary conditions, and solve for their values. Okay. Okay. So what are the boundary conditions here? Well, for a boundary condition, in order for us to define a boundary condition, we need a geometry. Right? Okay. So let's look at a typical blood vessel, right? And so our blood vessel here, right? It's like a 1D blood vessel. Okay. So we have two conditions here. So we have, you know, the condition at z is equal to 0. Okay, so the inlet of the vessel is going to be z is equal to 0. Okay, and if the length of the vessel is given by L, right, then our other boundary condition will be given by z is equal to L. Okay, so we need a boundary condition here and a boundary condition here. Okay, let's start with the inlet condition. So at the inflow here, okay, so at inflow, we're going to assume that the amount of inflow into the model is known. So the Q in is known. Okay, so you have Q1 at z is equal to 0 is equal to Q naught. Okay, So that's pretty straightforward and pretty consistent with our lump parameter model, right? So, for lump parameter modeling, we usually kind of know kind of what the inflow condition is, right? So that's our Q in, Q naught, or whatever we call it, okay? At the outflow, we're going to do kind of a very traditional kind of boundary condition for blood flow as well. We're going to assume that we know something called the terminal impedance. Okay. So we'll talk about the terminal impedance a lot more next time, but basically what we can say is that this quantity ZT, so this ZT here is our terminal impedance. Okay. Which again is going to be known. So that's either going to be given to you in the problem, or it's something that's kind of easily measured in the cardiovascular system. Okay. This is equal to the ratio of P and Q. Okay. Okay. So we're going to assume that that quantity there is known, the terminal impedance. Okay. Okay. So when we pick this up on Thursday, we'll kind of finish up this derivation here. We'll apply these boundary conditions and solve for all of the constants C1, C2. Okay. And then next class, what you'll see is how we can actually use this information, to find the impedance of the vascular tree. Okay. So, to give you guys a little bit of a preview, the last problem on the homework has to do with this stuff here. But because impedance itself is kind of a complicated phenomenon, we're going through all this trouble here to find these equations, and we're still, have imaginary numbers and things floating around. So the problem that I'm giving you on the homework is kind of a simplified version of this. So it's not as mathematically as intense, but it still kind of captures a lot of the same kind of the same kind of behavior. And so I think what I'll do next time as well, probably for the last few minutes, is that I'll kind of talk a little bit about that last problem on the homework assignment, because it is a little bit unusual, and kind of talk about how that kind of connects to everything that we've discussed so far. Okay. All right, so that's it for today. So thank you guys for coming, and so thank you guys for being flexible, for meeting virtually as well. I do plan on coming back on Thursday, so I will be back in the class, but the Zoom, but I will be streaming it on Zoom just as usual. Okay, so thank you guys for coming today. I hope you guys enjoy the rest of your day. Hope you guys have a good rest of your afternoon, and I will see you all on Thursday.